Welcome back. So we have designed the three counters in the previous videos. And now we will design a new kind of a counter wherein the count is explicitly mentioned. Let me pose this as a design problem so that we can proceed to solve it. So it is something like this. We have to design a counter that counts through the following states. So this is what I mean, that the sequence is mentioned and the states are, it has four states. The first one is 1 0 0 0, followed by 0 1 0 0, then 0 0 1 0, then 0 0 0 1, and then back to 1 0 0 0. So there are four states. Fine. Just try to differentiate between the way the problem is posed here. In the previous counters, the problem was kind of an implicit one, like consider the decimal decade counter. So it was kind of implied that the decade counter will start from 0, count one by one up to 10, then reset back to 0. Similarly, up counters and down counters that we defined, in that case also, the count was implied. But in this case, the count is explicit. It is given that the circuit should go through these four states, which are 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. And there's a kind of a logical relationship between the subsequent counts. If you start with the first stage, a first count 1 0 0 0, in the second count is actually obtained from the first one by shifting 1 to the right by 1 place. Then the third count again shifting by 1, fourth count again shifting by 1, and then reset back to the first count. This has a very important application in control circuits, and it's a very specific counter. I won't name it as of now, but if we first design it, then when we have this circuit, then we will see what we call this kind of a counter. So again, we'll start with the same procedure, where in the first step is we have to create the finite state machine. That's always the first step. Fine. So the first step is we create the finite state, we capture the finite state machine. Capture is a better word. We capture the FSM, and in this case it is pretty straightforward because the states are explicitly mentioned. So the FSM here would have four states. Like this. In the first state, we'll call it 1 0 0 0. Then it will move to the next state 0 1 0 0, then the next state, then the next state. Fine. And the transitions will happen for every positive clock edge, something like this. Fine. So this is the finite state machine for this circuit. Then our second step is we create the standard architecture. Again, this is a trivial step. Fine. Now here you have to be a bit careful. See, the states are explicit here, and every state is of 4 bits. Now you know that state actually means what is being stored in the state register of a sequential circuit. Now you may get confused that I have only 4 states here, and to code 4 states I need only 2 bits. But the thing is, the states are explicit here. You have been given the nature of the states, given the value of the states. And in actual practice, since these are 4 bits that represent the states, there are actually possibility for 16 different states. And out of those 16 different states, these 4 are the valid states for this particular counter. Right? What I'm trying to say is that we will have to use a 4-bit state register here because of the fact that the state values have been provided in the problem itself, and every state value is of 4 bits. So the standard architecture here would be something like this. It will have the combinational part as usual, which we'll have to resolve later, and it will have a sequential part. And this one will be my 4-bit state register. Obviously, it will have a clock Then from this state register, I will have 4 inputs: S3, S2, S1, S0. Fine. So let this be S3, S2, S1, S0. And then there will be the next states as usual. This is the usual occurrence for us. Say this is N0, N1, N2, and finally N3. Something like this. Fine. So this is N0, N1, N2, N3. So this will be the standard architecture. I'm again repeating, although there are only 4 states, but these are only the valid states. The total number of states is 16. Out of those 16, these are the valid states that are explicitly mentioned in the design problem. Fine. In the previous cases, we had to design the counter in an implied sense. We didn't have the explicit states, we just had a description about the design. So you have to be careful while dealing with these kind of circuits. Okay, so this is my standard architecture. Third part is we have to encode the states. Again, in this case, it has been already done because you know that every state has a specific code associated with it. So we don't need to encode it. It is already encoded. The fourth step is we have to create a state table. And in this case, it will be pretty straightforward to create a state table. We will have the previous state as S3, S2, S1, S0, and the next state N3, N2, N1, N0. Now with 4 variables, you can have 16 explicit conditions. But out of those 16 conditions, we have to consider only the 4 that are given. So if my current state is 1, 0, 0, 0, the next state is going to be 0, 1, 0, 0. Then when the current state is 0, 1, 0, 0, the next state is going to be 0, 0, 1, 0. Then when the current state would be 0010, next state will be 0001. And when it is 0001, it will reset back to 1000. Fine. So these are my 4 valid states. And apart from these 4 valid states, the remaining 12, they are invalid. And you know that when there are invalid states, you can actually exploit those states in terms of don't care conditions for simplification. But in this form, if I come up with the expressions, I will have, let me write it here, N3 will be equivalent to S3 complement, S2 complement, S1 complement, S0. Fine. Similarly, N2 will be equivalent to S3, S2 complement, S1 complement, S0 complement. N1 will be equivalent to S3 complement, S2, S1 complement, S0 complement. N0 will be equivalent to S3 complement, S2 complement, S1, S0 complement. Fine. But when we try to simplify them, we can exploit the don't care conditions. You could have actually demonstrated it from the state table itself also, because we normally take only those combinations for which my output is 1. This is what I have done here. N3 is 1 here. So this corresponds to S3 complement, S2 complement, S1 complement, S1 0, S0. So this is the term. Fine. Similarly, N2 is high only for this condition, which corresponds to S3, S2 complement, S1 complement, S0 complement, and so for N1 and N0. But to simplify them, we can actually take advantage of the don't care conditions. So I have drawn here 4 Karnaugh maps wherein the X mark is for the don't care condition. This one is for N3, only one cell is filled because only one term, min term appears in the expression. Similarly, this for N2, N1, N0. And you can see we can exploit don't care condition in each of these K maps and come up with a simplified expression for each of my Boolean outputs. Maybe I should shift it here like this. So these are simply assigned operators. There is nothing logical involved here. Fine. So this means if I try to, because the last step is after you have simplified these expressions, you implement the combinational logic. But in this case, it will be pretty strange. It will be, let me draw it here. It will be quite different here. So we have the combinational, we already know what our state register is. We have a 4-bit state register. So this is my, right here, 4-bit state register. And from this 4-bit state register, I had 4 outputs. I had 4 outputs, S3, S2, S1, and S0. Let me write them. S3. Fine. Now, as per these simplified expressions, my N3 is equivalent to S0. Fine. So that means this is my N3 and this is equivalent to S0. Similarly, my N naught is equivalent to S1. N naught is equivalent to S1. Then my N1 is equivalent to S2. And finally, my what you call S3 is equivalent to N2. So I'm not using any gates here to resolve my combinational logic. For your reference, this is N3, this is N0, this is N1, this is N2. Right? And obviously we'll have the clock. That's a given, huh? Fine. Now in this kind of a schematic, it doesn't make much of a sense. I mean, you're not able to actually visualize it in a proper way. So we'll do next thing, because no combinational gates are involved here. We'll actually resolve this in terms of the flip-flops, something like this. Fine. Because I told you that the basic storage cell that stores a bit is the flip-flop. So if you have a 4-bit state register, it is nothing but 4 flip-flops. Fine. So this is what I've drawn here. These are the 4 flip-flops. The first one I have called the flip-flop 1 with inputs D1, output Q1 and Q1 bar. The second one is D2 with outputs Q2 and Q2 bar. Similarly, D3 as the input for the third flip-flop with Q3 and Q3 bar being the 2 complementary outputs. Same goes for this. Fine. And this one, if I mark the inputs and the outputs, so input here is S3, output is N3. Fine. Sorry, it should be the other way around. Let me just rectify it, because I'm talking about the first cell here. So this is the input, which is N3, and this is the output, which is S3. Fine. So we'll draw it in that sense. So N3, S3, then N2, S2, N1, S1, N0, and S0. For the time being, I'll just remove this. Fine. And actually, I need a new connection. Okay, I can't remove this. We'll do one thing, we'll draw it afresh. So I need 4 flip-flops. This is one. This is the second one. Third one. And a fourth one. Fine. They will have a common clock. Let's first draw the clock. This will be the clock. So this is the clock here. All will have a common clock. Like this. So this is my clock. Fine. Then for the first flip-flop, we will have inputs D1 and the output as Q1 and Q1 complement. For the second one, D2 with the outputs as Q2 and Q2 complement. Then D3 with the outputs as Q3 and Q3 complement. D4 outputs Q4 and Q4 complement. Fine. Now the extreme left flip-flop, it has inputs as N3 and it will give output as S3. Then for the next one, N2, S2. Then this one, N1, S1. Then finally N0, S0. Now as per the solution, N0 is equivalent to S1. Fine. Then N1 is equivalent to S2. Then N2 is equivalent to S3, which means these are actually directly connected. This is connected to this. Just a second. This is connected to this. This is connected to this. And as far as S0 is concerned, S0 is equivalent to N3. So S0 from this side is connected to the input of the first flip-flop. So this is the circuit in terms of these flip-flops. Fine. Now you can see what actually is happening here. The output is directly connected. So it is kind of a ring kind of a thing. And in fact, we call this type of counter as a ring counter. Fine. Because it kind of ripples the output of the last flip-flop to the input of the first flip-flop. Now let's assume we have some clock cycles here. Fine. And let's say we have clock 0. And the contents of the 4 flip-flops are these 1, 0, 0, 0. Fine. So this is Q1, this is Q2, this is Q3, this is Q4. Now when the first clock comes, this output will be rippled here. Fine. So Q4 will appear at the Q1, so it will be 0. This will move here because of this connection. 1, 0, 0. Another clock comes, again there will be rippling, because every time a clock comes, there will be a transfer from one flip-flop to the next. You know that flip-flop are edge triggered and they the data at the input moves to the output for every rising clock. We have done that. So after second clock, it will be 0, 0, 1, 0. Then another clock will come, it will be 0, 0, 0, 1. And when the fourth clock comes, it will be again 1, 0, 0, 0, which is my initial state. So it's a kind of a ring kind of a thing. A kind of rippling is happening wherein the contents are being passed from one flip-flop to the next flip-flop, and finally from the final flip-flop, the fourth flip-flop, to the first flip-flop. And that's why it gets its name, the ring counter. Fine. Now if you observe that with a 4-bit ring counter, you will only have 4 valid states. So you can have only 4 valid states, which are these 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. And a modification of this ring counter is what's known as a Johnson's counter. It is the same thing as the ring counter with a slight difference, and the difference I will show it here is where it, okay, let me first draw the flip-flops here. So this is the first one, this is the second one, this is the third one, this is the fourth one. Now in a normal ring counter which we just studied, this is Q1, sorry, not Q1, D1. This is the input Q1 and Q1 bar. Then D2, Q2, Q2 bar, D3, Q3, Q3 bar, D4, Q4, Q4 bar. Now what happens in normal ring counter as far the intermediate connections are concerned, they are connected something like this. This is connected to this, this is connected to this, this is connected to this, and the last one was connected to this. But we are modifying the last connection. What we are doing now with the Johnson's counter is we are actually connecting it with the complemented output. Something like this. Fine. There obviously will be a clock. I am skipping that, but that is implied. So every flip-flop will have a clock, and they all will have a common clock. Fine. So that's a given thing. But I am making one change in the Johnson's counter, that instead of connecting the normal output from the final flip-flop to the first flip-flop, I am connecting the complemented output from the final flip-flop to the first flip-flop. The rest of the connections I am keeping the same. Now what it does is it gives me additional states in my counter. This is also a ring counter, but this gives me additional states. Let's again do that analysis. Let's have a clock here. Clock number here, then Q1, Q2, Q3, Q4. Clock 0, and let's initially assume that these are the values, which means this is 0, this is 0, this is 0, and this is 1. And because of the complementary nature. Now when the first clock comes, this one will be rippled here to the input. So Q1 will become 1, rest will be 0, 0, 0. Then second clock comes, again because of this complementary nature, 1, 1, 0, 0. Third clock, 1, 1, 1, 0. Fourth clock, 1, 1, 1, 1. Fifth clock, now this Q4 becomes 1, this becomes 0. So it will be 0, 1, 1, 1. Sixth clock, 0, 0, 1, 1. Seventh clock, 0, 0, 0, 1. Eighth clock, then it will come back to the original state. So you have actually doubled the number of states by making this small change. You can see state 1, state 2, 3, 4, 5, 6, 7, 8. So the normal ring counter gives you only 4 states. But if you make a small modification wherein you connect the complementary output of the last flip-flop to the input of the first flip-flop, it actually doubles the number of states. Instead of 4, for 4 bits, you can have 8 different states. And that's important. Like I said, these counters are used in the timing and control circuits of your microprocessors or microsystems. So the more the states with a given number of bits, the better it is. So this is the Johnson's counter, which is a modified form of a ring counter, with the difference that it gives you 4 states instead of 8 states instead of 4 states for a 4-bit counter. Right? So this is yet another counter that we have designed. We'll stop here.